Okay, a quick overview of semiconductors. A conductor has very good electrical conductivity. It's got free charges that can move when a potential difference is applied. For example, metals. They have loose electrons in the lattice and those are free to move. Another example are ionic solutions in liquids. Positive and negative ions are free to move. Graphite is another example, an odd example. It has very strong planar or 2V covalent bonds, but electrons are free to move in the third dimension. A non-conductor or an insulator has little or no electrical conductivity. There are few free charges. For example, ionic solids. Electrostatic bonds between positive and negative ions are very strong. Most covalent materials, such as diamond, have strong tetrahedral bonds. A semiconductor has some intrinsic conductivity. It has covalent bonded electrons, but some are loosely bonded. And at room temperature, conductivity is low. But as you increase the temperature, conductivity starts to increase, which is the opposite of what happens with metals. Okay. When an electron is removed from the covalent bond, it leaves behind a space called a hole. When a potential difference is applied, the electrons can move against the potential difference, and holes can move with the potential difference, like positive charges. Therefore, conduction is due to both negative electrons moving and positive holes moving. On the subject of doping, the conductivity of a pure semiconductor is increased by doping, that is, adding a small amount of some other impurity. It's an element to the left or the right of the periodic table, in the periodic table of silicon. For example, to the left you would get negative doping, and to the right positive doping, because of the number of valence electrons in those materials. To the left, group 3, and to the right in group 5. For negative type material, for example silicon, you could use phosphorus or arsenic to dope it and add an electron into the crystal structure. Adding an electron which is free to move increases the conductivity, so the conductivity will be greater than pure silicon. Current through this doped material consists almost entirely of the movement of negatively charged electrons in the opposite direction to the potential difference. For a p-type material, the opposite is done. You dope with a material such as boron or gallium. Okay. In this case, the current is almost entirely due to the movement of positively charged holes, which move in the same direction as the potential difference. A PN junction diode is a junction between some N-type material and P-type material. Upon the bonding of the two materials together, there is some initial flow of electrons to holes across there, and the result of that flow is that there is actually a zone of depletion where there are no electrons or holes available, and that is called the barrier zone, or barrier or depleted layer. And the potential difference applied across the chip from here and here, required to get across that area, is called the barrier potential. And for the usual semiconductors we're looking at, the barrier potential is about 0.6 to 0.7 volts. The characteristic voltage curve for a semiconductor. Note that we have different scales, microamps versus milliamps, and volts versus volts on that side there. Okay.